In today's session, we'll discuss some of the problems which are associated with the gas turbine cycles. Let us see what is the statement of this particular problem. The air enters the compressor of an open cycle constant pressure gas turbine cycle at a pressure of 1.01 bar and the temperature of 15 degrees Celsius. So I mean to say that it is the initial pressure of the air and initial temperature of the air that is given to us. The pressure of the air after compression, it is 4 times the initial pressure. Okay, so it is a pressure ratio for the compressor, in other words, that is mentioned to us. And while carrying out this expansion process, the compression process, while carrying out this compression process, the efficiency is mentioned as 82%. The air then passes through a heat exchanger heated by the turbine exhaust before reaching the combustion chamber. This is very important statement. It states that the air after compression passes through a heat exchanger and this air is heated by the turbine exhaust before the air reaches the combustion chamber. It means that you are using a heat exchanger after the compressor and before the air is getting admitted into the combustion chamber. So definitely this arrangement is used to improve the performance of the simple open cycle gas turbine cycle as such, and such arrangement that we will be calling as an regeneration. Okay, in the heat exchanger 78% of the available heat is given to the air. Okay, 78%. So in other words, this is nothing but the effectiveness of the heat exchanger that is mentioned to us, 78%. The maximum temperature after the constant pressure combustion, so that temperature is 600 degrees Celsius, and the turbine efficiency that is mentioned as 70%. And we have to neglect the various losses which are supposed to be taking place in the cycle, and so as to evaluate the network and the cycle efficiency. Okay, so let us initially draw the arrangement for the simple open cycle gas turbine plant which is provided with the regeneration arrangement. Okay, so before I proceed for the complete solution, it is essential for us to draw the layout from the given description, and let us plot the various processes on the temperature entropy diagram as well. Okay, so I will call this arrangement as such, their use as a regeneration. So regeneration is one of the method to improve the performance of gas turbine cycle. The other methods are nothing but the intercooling, which is used to reduce the work of compression. Second is this regeneration arrangement that we are discussing in this problem. And the another method that is important to improve the efficiency or to improve the performance of the gas turbine cycle, so that is nothing but the reheating. Okay, so let us initially plot the block diagram for the regeneration arrangement used in the gas turbine cycle. So I will start here with the, let us say, initially a compressor. Okay, so this is what a compressor is, and I will place here a heat exchanger that we call as a regenerator. Okay, or the regenerative heat exchanger. And after this heat exchanger, so air will be admitted in the, let us say, a combustion chamber. So I'll write down this as, let us say, a C, that is nothing but a compressor, and this is nothing but a heat exchanger or a regenerator. Okay, HEX, that is a heat exchanger I will call. This is nothing but, let us say, CC, combustion chamber. We will supply the fuel, and after the combustion chamber the gases will be allowed to enter into the turbine so that they can be expanded. Okay, so this is the turbine, gas turbine, and we'll have a common shaft which connects the compressor and the turbine. Okay, so let us say this is a horizontal shaft which connects the gas turbine with the compressor, and we are aware that this part of the power which is developed by the turbine, so that will be used to run the compressor, and the exhaust gases which are coming out of the turbine. Okay, so this way. Okay, so the exhaust gases, before they are left to the surrounding coming from the turbine, so they will be admitted into this heat exchanger and then left to the atmosphere, left to the surrounding, we can say. Okay, so let us give the appropriate numbers for the various state points. So state point 1, that will represent the condition of the ambient air, atmospheric air entering the compressor. Then I will give this a state point 2, which is coming out of the compressor or entering into the heat exchanger. Number 3, so that is where the air will be heated with the help of the exhaust gases coming from the turbine and before they are exhausted to the surrounding. Then state point 4, so after the constant pressure heat addition, I can say this point number 4. State point 5, the gases after the expansion coming out of the turbine. Okay, and 6, let us say the gases which are leaving this heat exchanger and then sent to the atmosphere. Okay, so let us plot this particular arrangement on the temperature entropy diagram also. Okay, various state points that I have represented on the block diagram. So if I am supposed to show this various processes on the temperature and entropy diagram, okay, TS diagram. So let us say these are the two constant pressure lines. Okay, let us say this pressure line P1 and this is, let us say, a pressure line P2. I will show the first process, let us say asentropic compression process. Okay, let us say 1 to 2 dash asentropic compression process, and I know that the asentropic efficiency of the compressor is given to me. So actual compression process will differ to 1 to 2 actual compression process. Then 2 to 3, let us say that is nothing but the heat which is utilized in the regenerator. Okay, heating of the air will take place before it is admitted in the combustion chamber. Then I can say the state point 4 after the constant pressure heat addition, and let us say 4 to 5 is the asentropic expansion of the gases in the turbine. Okay, I write down this as a let us say 4 to 5 dash rather. Okay, and the actual expansion will differ than the asentropic expansion, so let us say actual expansion is 4 to 5. Okay, so I hope that you have understood the block diagram that we have represented here and the various processes on the temperature entropy diagram. Okay, so let us see what the data that is given to us. So it is mentioned to us that the initial pressure, so that is given as 1.01 bar. Then the initial temperature of the air, that is T1. Okay, so initial temperature of the air, that is given as 15 degrees Celsius. I will convert that in Kelvin. Okay, I will add 273 into that one. So I will have the initial temperature as 288 Kelvin. Okay, pressure ratio, that is given as 4, isn't it? Pressure, the pressure of the air after compression, so that is mentioned as 4 times the initial pressure. Okay, after the compression it means that pressure P2, so it is 4 times the initial pressure, so 4 multiplied by this 1.01. Okay, so pressure after the compression, that will be 4.04 bar. Okay, very simple to understand. Pressure P2, that is nothing but 4.04 bar. Asentropic efficiency for the compression, so I will say eta C. So eta C is 0.82, that is 82%, that is mentioned. Then the effectiveness of the heat exchanger, okay, so that is mentioned as 78%. So I will write down as 0.78. Then what data that is further mentioned to us? The maximum temperature after the constant pressure combustion. So maximum temperature in the cycle that we can see is nothing but the temperature at point 4. Okay, so T4 is nothing but the T max. Okay, the process 3-4 is nothing but the constant pressure heat addition in combustion chamber. Okay, so that is the temperature T4 is nothing but the T max. So that is given as 600 degrees Celsius. So 600 plus I will add 273. So temperature will be then 873 Kelvin. Okay, 873 Kelvin. Turbine efficiency, that is also mentioned to me. So that is eta T. Turbine efficiency 70%, 0.7. And you are supposed to neglect any losses which are as such taking place. And we have to find out the W net. Okay, net work which is say obtained from the cycle, and the cycle thermal efficiency. Okay, cycle efficiency. So that indeed is nothing but the thermal efficiency. Now for our convenience, we will assume the gamma for the air as 1.4, and specific heat for the air, we will assume the specific heat of the air as 1.005 kilojoule per kg Kelvin, as these are not mentioned there in the statement. So it is safe to assume the value for the gamma equal to 1.4, and the specific heat at constant pressure Cp for the air as 1.005 kilojoule per kg Kelvin. Okay. So let us begin with the calculation part now. Okay. So I will move to the next part for the calculation. Now for the process 1 to 2 dash, that is the asentropic compression process. Okay. For the process 1 to 2 dash asentropic compression process. So I can write down that the temperature T2 after compression, that is T2 dash divided by T1, that is equal to P2 by P1, okay, which is the pressure ratio, P2 by P1 raised to gamma minus 1 divided by gamma. So this equation will help me to calculate the temperature T2 dash, temperature after the asentropic compression. I know the value of temperature T1 as 288 Kelvin, pressure as 4.04 bar, T2, pressure P1 1.01 bar, and gamma equal to 1.4. So if I substitute these numbers in the equation, so I will get the temperature T2 dash. So this temperature T2 dash is obtained as 428.13 Kelvin. Okay, please check the answer that you will get after the calculation. Okay, please confirm this. A temperature after the asentropic compression. Then the actual temperature after the compression, that can be known by using the compressor efficiency. Okay, so I can write down this asentropic temperature rise, that is T2 dash minus T1 divided by the actual temperature rise. So actual temperature rise is nothing but this T2 minus the T1. Okay, this compressor efficiency I am expressing as the ratio of asentropic temperature rise to the actual temperature rise. I know the compressor efficiency mentioned as 0.82. Okay, then I know the temperature T2 dash, I know the temperature T1, so only unknown is the T2. Okay, so substitute all these numbers and I will be in a position to calculate the temperature T2, temperature after the actual compression process. So this temperature is obtained as 458.89 Kelvin, temperature after the actual compression. Okay, now similarly for process let us say 4-5 dash, that is nothing but the asentropic expansion of the gases. Okay, 4 to 5 dash process. Okay, process 4-5 dash, that is the asentropic expansion of the gases in the turbine. Okay, so I can write down the equation, that is the T4 upon T5 dash. Okay, T4 upon T5 dash. So that is equal to P4 divided by P5. Okay, P4 upon P5 raised to gamma minus 1 divided by gamma. Right? Now if I see the temperature entropy diagram here, okay, temperature entropy diagram. So what I observe that the pressure P2 that is equal to pressure P4, and similarly the pressure P1 that is equal to pressure P5. Okay, these are the constant pressure lines. P2 that is equal to P4, it is indeed P3 as well, P2 equal to P3 equal to P4, and on the other side it is P1 that is equal to P5. Okay, so I hope that this pressure that you understood, the values of the pressures are understood there. Okay, so by substituting the appropriate numbers here, I know the value for the temperature, that is nothing but what I can say, T4 that is known to me. Is it known to me? The temperature T4, yes, it is nothing but the T max 873 Kelvin. Okay, temperature T3, T4 is known to me. Temperature T5 dash that I have to evaluate. Pressure P4 is known to me, pressure P5 is known, and gamma is also known. Okay, so by substituting the all the values for the T4, then P4, P5, gamma, so only unknown is nothing but the temperature after the asymptotic expansion of the gases T5 dash. Okay, so I will evaluate the temperature after the asymptotic expansion T5 dash as 587.25 Kelvin. Okay, that will be the temperature T5 dash. Okay, now I will take into consideration the turbine efficiency to determine the temperature after the actual expansion. Okay, so turbine efficiency that I can express as the actual temperature drop, okay, that is the T4 minus T5 divided by the asymptotic temperature drop, that is T4 minus T5 dash. Okay, for the turbine efficiency I can express it as the ratio of the actual temperature drop and the asymptotic temperature drop. So I am having the turbine efficiency as 70%, the temperature T4 as 873 Kelvin T max, and the temperature T5 dash just I have calculated as 587.25 Kelvin. So if I substitute all these numbers in this equation, so I can calculate the temperature after the actual expansion, that is T5. So T5 is obtained at 672.98 Kelvin. Temperature T5, that is temperature after the actual expansion of the gases. So from this exercise, I know the temperature at various salient points in the cycle, and that will help me to calculate the compressor work, because I know that this W net, okay, I want to evaluate the W net. So W net is nothing but the turbine work minus the compressor work. Okay, work required for the turbine, or the work which is developed by the turbine, and we need to subtract the work supplied for the compressor. So I can calculate the work for the compressor, that is WC, okay, per kg of the air circulated. So that is Cp into T2 minus T1. Okay, compressor work that can be calculated as per kg of the air, Cp into T2 minus T1. Cp that I have assumed as 1.005 kilojoule per kg Kelvin. Temperature T2 I have evaluated as 458.89. Temperature T1 that is given to us as 288 Kelvin. So if I substitute all these values in this equation, so I will obtain the compressor work as 171.74 kilojoule per kg of the air. Okay, so this is nothing but the compressor work. I need to evaluate the turbine work as well. Okay, so let me add one more page here. Okay, just a minute, please hold on. I will add one more page in this particular slide there. Let me add one more page. Yes. Okay. So we have added one more page here. We are interested to calculate the turbine work now. So the turbine work, that is WT. Okay, turbine work. So per kg of the air circulated, so I can write down the Cp into the temperature T4 minus the temperature T5. Okay. I know the Cp, that is 1.005 kilojoule per kg Kelvin, temperature T4 as 873 and temperature T5 as 672.98. Okay, so these were the values that I have evaluated in the previous part there as such. Okay, so if I plug in all these numbers in this equation, so I obtain the turbine work as 201.02 kilojoule per kg. Okay, so this is what the turbine work which can be obtained. And once both of these works are obtained, turbine work and compressor work, then I can write down the W net, so which was the first unknown as such. Okay, so turbine work minus the turbine work minus compressor work, so that is the 201.02 turbine work minus the compressor work that was evaluated as 171.74. So hence the net work is obtained as 29.28 kilojoule per kg of air. So this is what the first required unknown. Okay, this is the answer, the first part. Similarly, we have to determine the thermal efficiency of the cycle. Okay, second unknown. So thermal efficiency, so we can write down it is a ratio of the net work divided by the heat supplied, and you multiply it by 100 to get the efficiency, that is in percentage. Okay, W net divided by the QS, a heat supplied. So from the temperature entropy diagram, it was seen that the heat was supplied during the process 2 to 3. Okay, heat is supplied during the constant pressure process 3 to 4 rather. Okay, I'm sorry, the heat is supplied during the process 3-4. So heat supplied per kg of the air, so that is a Cp into T4 minus T3. Okay, the process 3-4 in the thing but the isobaric heat addition. I know the value for the Cp, I know the value for the T4, but I don't know the value of temperature T3, temperature of the air before it enters the combustion chamber. Okay, or that is nothing but the temperature of the air which is coming out of the regenerator. So let me elaborate how to calculate this temperature T3. So this is what the regenerator that is given to us, and which basically is nothing but, let us say, a counterflow heat exchanger. This is nothing but a counterflow heat exchanger. we are having this stream as, let us say, the air that is getting passing through this stream. Okay, air passes through this particular stream, and in the opposite stream another stream which flows in the opposite direction. So it is nothing but the hot gases which are coming from the combustion chamber, or which is coming from the turbine rather, not the combustion chamber but after the turbine. Okay, so it is the counterflow heat exchanger. We know that the temperature of the air which enters into this regenerator, this heat exchanger, is the temperature T2, and temperature which is leaving of the air is nothing but the T3. Similarly, the temperature of the gases after the expansion and entering into this regenerator, that is temperature T5, and gases which are leaving this regenerator is nothing but the temperature T6. Okay, so it is the temperature T6 rather. And if I show the arrangement for a counterflow heat exchanger again, okay, temperature and the area of, let us say, temperature, let us say, on y-axis, and the area which is there for the heat exchanger, a counterflow arrangement. So a temperature of the air, so that will increase, okay, from the initial value T2 to the temperature T3, and there will be the flow of the gases coming from the turbine in the opposite direction, so which enters at temperature T5 and leaves at temperature T6. Okay, so we have seen this particular configurations in the heat exchanger, okay, unit which is for the heat exchanger. So it was mentioned that the effectiveness of the heat exchanger is 78%. Okay, so epsilon is nothing but the effectiveness of the heat exchanger. So from this temperature and this area diagram that I have drawn, so I can write down the actual temperature rise for the air. Okay, that is T3 minus T2. So that is the actual temperature rise for the air, and it is divided by the maximum possible temperature rise for the air. So maximum temperature rise for the air will be T5 minus the T2. Okay, the maximum possible temperature of the air leaving the regenerator, so that will be equal to the T5. Okay, that is coming out of the regenerator and entering into the combustion chamber, I meant to say. So I know the effectiveness as 0.78, temperature T2 that I calculated as 458.89, temperature T5 that is known to us as 672.98, temperature T2 is known, so only unknown is the temperature T3. Okay, so I will just write down these numbers here. So effectiveness is 0.78, temperature T3 I want to calculate that, temperature T2 that we have calculated in the initial part of the calculation, so 458.89 Kelvin divided by T5, so that also we evaluated as 672.98 Kelvin minus T2 as it is 458.89. Okay, so make the calculations for this one and find out the temperature T3. So I calculate the temperature T3 as 625.88 Kelvin. Okay, please check these numbers with the proper calculations as well. So temperature T3 is known to us, so it is possible for us to determine the heat supplied during the constant pressure heat addition process. So QS, heat supplied, so Cp 1.005 kilojoule per kg Kelvin. Temperature T4, so that was the temperature T max 873 Kelvin. Okay, and minus the temperature T3, that is 625.88 Kelvin. So we can find out the heat supplied as 248.35 kilojoule per kg. Okay, so that is the heat supplied in the gas turbine cycle. And now coming to the last parameter, last step of the problem, thermal efficiency, W net. So net work we calculated as 29.28 kilojoule per kg and divided by the heat supplied, so that is the 248.35 and multiply by 100. Okay, so I will get the percentage efficiency of this regeneration cycle in the constant pressure gas turbine arrangement. So that is obtained as 11.79 percentage. Okay, so that is the thing, but your required answer. So I hope that you have understood this exercise. So this exercise was dealt with the simple gas turbine cycle, and it is provided with the arrangement of regeneration. Okay. In the next sessions, we'll see some of the exercises associated with the intercooling arrangement as well as the reheating arrangement. They are used to improve the performance of the gas turbine cycle. Okay. So thank you very much for your kind attention.